morning, everybody. Thank you, first of all, for the introduction, and thank you for inviting AP Sensing and also myself to contribute to this webinar about distributed acoustic sensing. So today's presentation is the second one in the series of this webinar. The first one was held yesterday and focused on the basics of glass fibers, because glass fibers form the basis of distributed acoustic sensing. That's why it made sense to first discuss glass fibers. And now in the lecture today, but also in the lecture tomorrow, I take the next step and try to explain how glass fibers can be used as sensors for acoustic waves. Besides explaining the concept of distributed acoustic sensing, I will aim at giving a brief insight into dust data as well, and will highlight a few examples for applications where distributed acoustic sensing can be used, but this will be part of tomorrow's lecture then. So before I start, I think it makes sense if I just quickly introduce AP Sensing and myself. AP Sensing is a German manufacturer of distributed fiber optic sensing solutions, and it is located in southern Germany, close to the city of Stuttgart, which is known for Mercedes, Bosch, and other big companies. AP in AP Sensing stands for Advanced Photonics, and this reflects our expertise in photonics, so the science of generating, controlling, but also detecting photons, which are basically light particles. We at AP Sensing, we use this expertise in this technology to develop distributed sensing, digital and service solutions, and we use this expertise to provide solutions to various industries across the different continents, and for monitoring and for measurements. The history of AP Sensing actually goes back until 1939, when Hewlett-Packard was founded in California. Nowadays, Hewlett-Packard is well known for printers and for computers, but this was not always the case, because originally Hewlett-Packard was a measurement technology company. But the measurement business of Hewlett-Packard was spun off into Agilent a couple of years later. And then the fiber sensing business from Agilent was spun off into AP Sensing. And this happened in the year 2007 and marked the foundation of our company. Today, AP Sensing is globally positioned. So that means we have global customers from all over the world. And we not only execute projects, but we also support our customers across all time zones and in many languages worldwide. So this is all about AP Sensing. I wanted to say regarding myself, I am working with AP Sensing. I have been working with AP Sensing for more than 4 years by now in the role of a project engineer. And as a project engineer, I execute customer projects. So that means I am in direct contact with the customer. I travel on site for taking into operation the DAS system or give remote technical support if needed. Well, that's all I wanted to say about myself. I added a few more comments to this slide about AP Sensing, but I leave it to the audience to go through this slide in the aftermath of today's lecture. So I just skip this slide for now. It is my understanding that the spectrum of the participants in this course is very broad. Everyone has probably his or her own background, comes from a different industry. And at the same time, I guess many of the participants are working in the field of exploration, mining, and seismic research. So given this diversity, and because everyone in the audience might have a different level of knowledge about distributed acoustic sensing, my presentation is aiming at giving a basic introduction to this technology. We just don't have the time to go into all the details. So my aim will be to give you a basic understanding of the technology. And in this way, I think we can make sure that if the basics are well understood, then we can, if we have the time, we can move on to more advanced questions and in case questions arise at all. So having said this, I would like to start my presentation with a motivation, with a teaser. Why is distributed acoustic sensing so nice? Why am I fascinated about this technology so much? I would like to present two examples to that end in very simple pictures. Why distributed acoustic sensing is beneficial for many applications. Also for the seismic research area. And my first example is one that I think everybody can relate to, regardless of his or her background. And it deals with monitoring train tracks. So railway operators worldwide face the task to ensure that the train tracks are in good condition. That's important because health monitoring of train tracks ensures that people do arrive safely at the destination, that goods are delivered in time, and also that maintenance costs can be kept to a minimum. So health monitoring of train tracks is important. But how actually can you achieve this goal? How can you monitor train tracks? Because train tracks are not only do not only exist in big cities, but you also have them in remote places where nobody lives nearby. So how can you make sure that at any point of time, you know whether your train tracks are in good condition? The conventional approach, or basically, so what are the threats to train tracks at all? I should mention first. There are actually multiple threats to train tracks. Some of them are listed in this slide here. So for instance, there are rail breaks. So rails can break because of fatigue, defects, or repeated stress. Natural hazards can happen. Train tracks can be buried by mudslides or rock slides. But also the condition of the ground below the rails can be bad, so that sinkholes can occur over time and destabilize the rails. Each of these events, rail breaks, natural hazards, and bad condition of the ground, each of these events can cause a train to derail and therefore can lead to a major accident. And of course, it's obvious then that one would like to be warned as fast as possible, as soon as possible, if such an event occurs, in order to initiate countermeasures and to eliminate the risk as fast as possible. So these are real threats railway operators are dealing with. It's just now the question, how can you assure that at any time your train tracks are in good condition? The conventional approach, which has been used so far, is straightforward, but also I would say sort of complicated, because how do you get to know that your train track is defective? Well, either a train driver reports notes some suspicious observation while he moves on the train track. And if he makes such a suspicious observation, then he reports it, and somebody needs to go there and check the train track. The second method is that train tracks are inspected by personnel regularly. So that means that you have people who walk along the train tracks and they visually inspect the train tracks for damages. Or you employ special train tracks that are measuring, you're employing special trains equipped with a certain measurement technology that then measure the geometry of the rails. So these are the conventional approaches how train tracks are monitored nowadays. All of them share the same disadvantage, because if there is a defect, you don't get to know it in real time. You only know it if some train driver notices it. If a train arrives on site, then it's already too late. So how can you monitor the health of train tracks in real time? And a solution to this problem can be, or is actually, distributed acoustic sensing. So distributed acoustic sensing means we connect a DAS system to a glass fiber, which is already installed right next to the train tracks. And by connecting a DAS system to a glass fiber, you turn the glass fiber into a microphone. And this microphone then listens to suspicious acoustic signals in the earth close to the train track. And if such a suspicious signal is recognized, the DAS system can send a warning or an alarm in real time to the operator of the railway. So this is one example where distributed acoustic sensing is helpful. The second example I want to share with you is more focused now on seismic surface measurements. If you want to study seismic, or if you want to conduct seismic surface measurements, then one of the conventional approaches is to use geophones. Geophones are vibrational point sensors, and if you conduct a surface measurement, then you install these point sensors a few meters or a few 10 meters apart from each other. You use a vibrotrack to generate some acoustic waves, send them into the ground, and the different layers in the ground, they reflect the acoustic waves differently. They are reflected back to the surface where the geophones detect them, and from this data, then you can get information about the structure of the ground. Again, how can one use distributed acoustic sensing here? Because we also have to do it with acoustic waves in this application. So the DAS approach for seismic surface measurements would be that you use an existing glass fiber cable that is already buried in the ground, or you deploy one on your own. And again, you connect a DAS system to the glass fiber, and you turn the glass fiber into a microphone. But the big difference here is now that the glass fiber covers the surface continuously. So you don't get any blind spots. You don't have the discrete spatial sampling like with geophones, but you have a continuous spatial coverage. Moreover, if you use existing glass fibers, the field logistics will be minimum. If you have to deploy your own glass fiber cable, it's still not complicated to do. But also important to mention is if you want to repeat the same measurements at different times in a year, then you can just leave the glass fiber cable buried in the ground, unattended, and come in a year or in a few months again, and the sensor has not been touched, so is still at the same position as before. So these two examples hopefully highlight that DAS technology is a useful technology, and that it has many benefits. And that's why it's the topic of today's lecture. For the distributed acoustic sensing technology, you basically need only three things. What you need is a sensor, which is a glass fiber. You need a method to read out the signal from your sensor. For this, we are using laser light. And then you need an analyzer that transfers, that converts the signal into useful data. These three things you need: the sensor readout, and an analyzer. And having mentioned these 3 points now, actually, I basically told you the outline of my presentation. I will first focus on the sensor itself, so on the glass fiber cables. I will then move on to the sensor readout, so explain to you how we can read out the signal of the glass fiber. So basically, it's an introduction to the DAS technology. And then at the end, I'm showing you a quick live demonstration just to highlight that DAS is working. But tomorrow, then we will focus more on the theory and have a closer look on the data itself. So today, the point is to explain the DAS technology and to see it once in a live demonstration. As we learned yesterday, glass fibers are deployed in many places nowadays. They are deployed in submarine power cables, for instance, for telecommunication between different countries. Glass fibers are deployed next to train tracks for communication. They are deployed in overhead power lines or in inner cities. They also are often installed with oil and gas pipelines. So there are many places where glass fibers are already deployed and can be used for DAS technology. And despite the fact that glass fibers are so crucial for our everyday life, I've met the experience that actually many people have never seen a glass fiber or a glass fiber cable. So for this reason, I thought I would like to start my presentation with an example image of how a glass fiber cable can look like. Of course, there are many different variations of glass fiber. So this is just an example picture of how a glass fiber cable can look like. In this image, you see that the glass fiber is in the center of the cable, and then you have multiple layers around the glass fibers. Basically, the idea of having these different layers is to protect the glass fiber and to support structural strength to the cable itself. There are different glass fibers you can get. There are single mode glass fibers. There are multiple glass fibers. You can get your cable with a single glass fiber inside. You can get your cable with multiple glass fibers inside. You can get your cable with an armor. You can get it as loose tube or tight buffered variation. So there are many different variations. And if you want to use one, then you need to inform yourself about what you actually need. But this is a general picture of how a glass fiber cable looks like. If you strip off all the outer layers, then you're left only with the glass fiber. And that's what I want to have a closer look at now. So the glass fiber itself consists of two parts. It's a central fiber core. That's actually where the light is traveling. And the fiber core is surrounded by a fiber cladding. The cladding is required to keep the light from escaping the core. The core has a diameter for a single mode fiber. The core has a diameter of 9 micrometers, and the cladding has a diameter of 125 micrometers. Single mode fibers are most often used nowadays, and that's why I will focus today on single mode glass fibers. The top right image shows you the cross section of a glass fiber. It consists of a fiber core and fiber cladding. Both are made out of glass material. However, they have slightly different refractive indices, and by these different refractive indices, we can guarantee that the light is confined to the core. If you have a look to the glass fiber now through a fiber microscope, then you end up with such images shown in the top right, in the bottom right corner. So here I took two example photos through a microscope, through a fiber microscope. In the left one, you can see a dark fiber. So it's a fiber where no light is propagating. And in the right image, you see a photo of a fiber where, actually of the same fiber where light is propagating. And you can see that the light actually is only visible in the very center of of this blue circle. And this is exactly the core, the fiber core. So this is how a glass fiber looks through a fiber microscope. Now, if we zoom in even further, namely to the fiber core itself, then there are also a few things to say. Namely, if you send laser light through the fiber core, then it gets attenuated with longer and longer distance. For single mode fibers, the attenuation is typically on the order of 0.2 dB per kilometer at the wavelength 1550 nanometer. So the attenuation is wavelength dependent and has a minimum at 1550 nanometers, and that's why many applications are using this laser light. Not all of them, but many of them. Not everybody is familiar with the expression of dB per kilometer, so I also put the numbers in linear terms here. So having an attenuation of 0.2 dB per kilometer means that you lose 4.5% of power per kilometer. And in other numbers, that means after 15 kilometers, you only have half of the initial power. The main reason why we have this attenuation along glass fibers is because of scattering. Scattering means that incoming laser light is scattered in different directions by scattering centers, and these scattering centers are present in the fiber core. This is what you can see here in the bottom right. So I show here the fiber core only, which is made out of fused silica. This material has scattering centers, and if the laser light hits these scattering centers, then a small portion of the light is being scattered in the backwards direction, and the larger fraction of the laser light is moving in the forward direction. So these scattering mechanisms, they lead to the attenuation. And it's funny to note that for many glass fiber operators, they don't want to have attenuation because that means that's what's limiting their range. But for distributed fiber optic sensing solutions, this backscatter light is actually what we rely on, because this backscatter light contains all the information we are looking for. So keep this in mind. I will come to, I will speak about this later again, but these scattering centers are relevant for us for DAS. So having said this, this is everything I wanted to mention about glass fiber. It's just a small repetition from yesterday's lecture, and this brings me now to the DAS technology itself. So the basic measurement concept of distributed acoustic sensing is as follows. So you have a glass fiber which acts as a sensor, and then you connect a DAS system to the sensor cable. The DAS system sends short laser pulses into the glass fiber. Each laser pulse has like a duration of on the order of nanoseconds, so it's a very short laser pulse. And these laser pulses are sent into the fiber and then travel to the very end of the fiber. Typical pulse rates that are used can be hundreds of pulses per second, can be thousands of pulses per second, can be 10,000 pulses per second. Each laser pulse that is sent into the glass fiber travels along the fiber and then leaves the fiber at the very end. On its way to the other end of the glass fiber, it scatters light in backwards direction. Every millimeter, every micrometer, every nanometer, a small portion of the light is being scattered in the backwards direction, and this backscattered light is now traveling towards the DAS system. And there, the DAS system receives the backscatter light and analyzes it for frequency, for amplitude, and for event location. So let's have a closer look at the backscatter light. The laser light we are sending into the glass fiber is actually originates from a narrow line width laser. Narrow line width means it has its spectrum is very much centered at the wavelength of 1550 nanometers. However, if you look at the backscatter signal that is detected by our DAS system, then the frequency spectrum of the backscatter signal looks much different. It has side peaks. Actually, it shows wavelengths that weren't there initially. And these side peaks, they come from different scattering mechanisms. So in the graph on the right side, you see that in this chart, in this image here you can see that the incident light pulse only contains this center wavelength here. However, then scattering mechanisms always also lead to lower wavelength and higher wavelength. And these scattering mechanisms are called Brillouin scattering. They are called Raman scattering. But for DAS, only the Rayleigh scattering mechanism is important. And Rayleigh scattering means that the backscattered wavelength is the same as the incoming wavelength. So there's no wavelength shift for Rayleigh backscattering. Okay, now one information we derive from the backscatter signal is the event location. If something is happening along the fiber, one information we want to gain is where is it happening? And how do we now get this information, where the activity is happening? And this is actually pretty simple to understand, because what we are doing is we are just measuring the time from injecting the laser pulse into the fiber until the backscatter light returns to the DAS system. So we are measuring the round trip time. This is similar to an radar echo. And radar echo sends a signal into the atmosphere. If there's an object, then the object reflects the signal. And by measuring the round trip time, you can then calculate how far the object is away from your antenna. For the DAS system means we are measuring the round trip time of the light. And from this, then can calculate the fiber position where the activity is happening. That's not rocket science. Actually, what you need is only two equations. I put those equations in this slide here because they are so simple. You need the formula for constant velocity, and you need the definition of the refractive index. If you insert equation 2 into equation 1, then you end up with this equation on the right side. And that's how we determine the location of events. So I mentioned that distributed acoustic sensing is used for recording acoustic signals. And then one question that can arise is, well, actually, what sort of frequencies can we detect? Is there a limit to the frequency range? What's the acoustic bandwidth of a DAS system? And that's what I want to discuss on this slide. So the acoustic bandwidth, so the frequency range we can detect with a DAS system depends on your settings. Most importantly, it depends on the pulse rate you have chosen, so the rate with which you are sending laser pulses into the fiber. And the reason why the acoustic bandwidth depends on the pulse rate is because there's a fundamental requirement to the DAS technology. At any point of time, there must only be a single laser pulse in the fiber. If there are multiple laser pulses in the fiber, you cannot distinguish what backscatter light is coming from which laser pulse. So you need to make sure that at any point of time, there's only one laser pulse in the fiber. And that means the next laser pulse can only be sent into the fiber after the backscatter light from the previous laser pulse has arrived at the interrogator. So imagine you are having a 10-kilometer long fiber, you connect a DAS system to it, you send in a laser pulse. So the laser pulse first needs to travel all the 10 kilometers to the very end of the fiber. And then the backscatter light from the other end needs to travel back to the DAS interrogator. And only then you can send in the next laser pulse. And now it's easy to see that the longer your fiber is, the longer it takes the pulse to travel to the very end of the fiber. And that means the longer your fiber is, the lower your pulse rate can be. So that's already one point to mention here. The maximum bandwidth you can record depends on the fiber length. Now, acoustic waves are analog signals, but we sample these acoustic waves only 1,000 times per second, 100 times per second, depending on your setting. So that means we are converting an analog signal into a digital signal. We are sampling the signal. And whenever you are sampling a signal, you need to consider the Nyquist theorem. That means the Nyquist theorem says you can only reconstruct a continuous time signal from its digital samples if the sampling rate is at least twice the highest frequency component of the signal. In our case, the sampling rate is the pulse rate. Whenever we are sending in a laser pulse into the fiber, we are sampling, we are interrogating the fiber. So that means if we send in laser pulses at a rate of 10 kilohertz, 10,000 times per second, then according to the Nyquist theorem, the maximum acoustic frequency I can detect with that pulse rate is exactly half of the laser pulse rate, so will be 5 kilohertz. Now, on the right side of this slide, I'm trying to summarize this information. So the diagram on the top tells you or gives you an impression what is the maximum detectable frequency depending on the total fiber length. And you can see the longer the fiber, the lower the maximum detectable frequency, because it's just the round trip time takes longer and longer. In seismic applications, you most likely have to do with short fibers. For instance, in borehole measurements, you typically have short fibers, so let's say 5 kilometers. Then if you have a fiber of 5 kilometers length, the maximum pulse rate that can be used is around 20,000 times per second. So that means we are sending 20,000 laser pulses per second into the fiber. And that means the maximum acoustic frequency that we can reconstruct from that data is around 10 kilohertz. Okay, so DAS is measuring acoustic waves. And basically, what you can effectively say is we are measuring changes in the local length of the fiber. So whenever something affects the glass fiber and stretches or compresses the glass fiber, so changes the local length of the glass fiber, that's something we can detect with our DAS system. There are three causes that can lead to a change in the local fiber length. There can be external mechanical forces. So for instance, imagine your fiber optical cable is deployed in the ground and you have an earthquake or you have a train passing by. Then these events generate acoustic waves, and these acoustic waves, they stretch or compress the fiber locally. So it's a mechanical deformation of the fiber. Another example could be if you have your fiber cable deployed in the sea, on the seabed, then a rising water level increases the water pressure on the cable. So that means the fiber optical cable will be squeezed, which is also a deformation. And this deformation can also be measured. So we have longitudinal deformation and we have transverse deformation. But that's not the only, these are not the only two reasons that can lead to a local fiber length change, because there's also temperature. If you heat up the glass fiber, then the glass will expand. And expansion means you have a change in fiber length. So that means we can also measure changes in the temperature, because this leads to a change in the fiber length. Okay, so to put it in simple words, DAS is all about measuring changes in the fiber length. And how DAS data is often presented in the form of waterfall diagrams, as shown in this chart. These waterfall diagrams are typically showing acoustic energy. So that means that they basically represent, they show you at what fiber positions do you have loud events, so a lot acoustic energy going on. At what fiber positions do you have a low acoustic energy? And all this is shown with different colors. So typically red means that at this current time and at this fiber position, you have strong activities right now. Blue means there are weak activities. The diagram I'm showing you right now on the right side is actually from a fiber optical cable that was deployed right next to a train track. And you can see that basically we have two kind of signals. We have these diagonal signals. These are signals that are moving because the vertical axis is showing time. The horizontal axis is fiber position. And you see if time passes by, this activity moves to the left side. And then we have signals that stay at the very same fiber position. These are static events, so that they remain just at the same fiber position. And what you can see here is actually trains moving along the train tracks. So these waterfall diagrams are sort of an acoustic heat map. You see when something happened, when acoustic energy was present. But what they do not show you is the underlying wavefront. So they don't show you how the acoustic wave itself actually propagated in the ground. If you are interested in this data, this is called phase data. This will be topic of tomorrow's lecture. So, but for now, I almost reached today's goal. I have explained to you, I have outlined to you the measurement concept of DAS technology. I have explained to you how DAS results can be displayed in diagrams, like in this acoustic energy diagram. I now would like to do a live demonstration and show you how DAS technology works in real time. So to that end, I need to share another screen. Now you should see the new screen,
good.
right?
It looks good. It looks good.
Okay, so short explanation, what can you see here? You can see the DAS system from AP Sensing, and there is a glass fiber connected to the DAS system. I just move quickly to my setup, and then I show you with the camera what I have prepared. So we have our DAS system here, and I have connected the glass fiber, this yellow cable, to the back of the DAS system. This glass fiber goes from the back of the DAS system to this chair. So we have the glass fiber here. This is 1,000 meters of glass fiber. Then we go from this glass fiber spool onto another 50 meters of glass fiber, and we have glued it here to the table. And after the table, there is another spool of 1,000 meters of glass. So this is the setup for now. The glass fiber is glued to the table. So that means when I start deforming the table now by knocking on it, then we are introducing deformation, mechanical deformations to the glass fiber, and then we should see a signal in our acoustic waterfall diagram. And to be able to show both of you, so if I'm correct, you should see the waterfall diagram right now. Is this?
Yes, yes, we are seeing it.
Okay, so as I just told you, I have connected a 1,000 meter spool, then a 50 meter spool in series, plus an additional 1,000 meters of glass fiber. So in total, we have something like 2,050 meters. These 2,050 meters of glass fibers are displayed on the horizontal axis. On the vertical axis, we have the time. Everything which is happening right now appears on the top. Fiber locations with large acoustic energy are displayed as red, and those positions with weak acoustic energy are shown as blues. Now, the table is positioned to be in the center of my setup. So the moment I start knocking on the table, I should see a signal at 1,000 meters, which is actually right in the middle of the screen. So if I walk to the table again, you can see me walking already, but I want actually I want you. I want that you see both simultaneously. So okay. So I now walk to the table, and this already generates enough signal to shake the glass fiber. Now I stop, and the signal will vanish again. So now I knock on the table, and you see the knock right in the center of my fiber length. If I knock 3 times, we see 3 signals. That's actually already a pretty strong signal. I am knocking quite hard. I can also do it more gentle. It's also still giving a very strong signal. So you can see it's a very sensitive technology we can see here. That's why I'm so fascinated about it.
There is a question, Philip, if you can hit somewhere else along the fiber, but I think your fiber is rounded, right? So
Say it again.
there is a question if you can hit somewhere else than in the middle.
Yeah, sure. So what I can do, for instance, I can touch the fiber right after the interrogator, so at a 0 meter fiber position. If I do this, then we get a signal at the very beginning. Right? I can also walk now to the second spool of my setup, so the last 1,000 meters. If I shake this entire spool, then of course you will see a signal across the entire 1,000 meters because I'm shaking the entire spool. Okay, basically, this is everything I wanted to show today. How the basic concept of DAS technology, and to introduce you to the waterfall diagram. As I told you, the acoustic energy diagram doesn't show you any information about the underlying wavefront. If you are interested in the wavefront, then you need to look at the phase data. And this is a bit more complex of a topic. So that's why we split this lecture into two parts. And this will then be dealt with tomorrow. But as a last information I want to share with you is real-world example data from activities, so that you can get an impression how this looks like. To that end, I am sharing another screen. I'm going back to this screen here. And I show you these images. So what you can see here is acoustic energy waterfall diagrams of different activities recorded with a DAS system. For instance, we have recorded in the top left, we have recorded an excavator digging. We have somebody climbing over a fence when the glass fiber was installed to a fence. We have here a person walking along a glass fiber cable, which is buried in the ground. We have train traffic if the glass fiber is installed right next to the train track. We can detect leakages in power pipelines, gas pipelines. We can also detect earthquakes by looking at glass fibers of submarine power cables. So all sort of things can be detected. And if you look closer to the data, if you look at the phase data and then look at how the signature of these different events look like, then you can apply artificial intelligence to the data and find this data, use this data for real-time monitoring of infrastructure. That's one example how DAS technology can be used. Okay, that's from my side. Are there any questions?
Thank you, Philip. Very, very instructive. So we got some questions. So I'm reading it from the chat box. On the slide 16, how is the attenuation calculated from dB kilometer to percentage per kilometer?
Yeah, that's a good question. Here. Yeah, so so dB is a relative measure. So you're comparing two quantities with each other. And if we talk about laser power, then there is a simple formula which can be used to calculate this. And The formula is basically 10 times the logarithm of the fraction power in divided by power out. That's the formula. If for power, if you apply this formula for amplitudes, then it's a factor 20 instead of a factor 10. But that's how you can calculate it.
So we have yeah.
So basically, it's now hard to explain it in words. So the answer is correct. I think I will prepare a brief slide for tomorrow's meeting where I explain this and show the formula, and then maybe it's easier.
Great. And then there's a question: if we have 50% of power, laser power drop per 15 kilometer, how much fiber cable can be deployed?
Yeah, it's a good question. So, this, I think the question is aiming at what is the maximum range you can monitor and still get a signal. And this depends on the application. If you are looking for very loud events, like if you are looking for cable faults in a power cable, if a power cable has a fault, what can happen is that it can explode. So this is a very loud event. If you are looking for these sorts of events, then you can go up to 100, 150 meters or longer. So if you're looking for faint signals like person walking or so, then the measurement range is will be shorter. So it depends on the application.
But a follow-up question, Philip, could you not use a stronger fiber, a laser pulse then?
Yeah, that's also a good question. And actually, I was thinking about preparing a slide on it, but then I left it out. So not really, because if you increase the laser power, what happens is that nonlinear effects will arise in the glass fiber. So that means the light is an electromagnetic wave, right? If you crank up the laser power, then the light field in the glass fiber will get so strong that the interaction with the glass material will lead to nonlinear effects, and these effects then disturb your signal.
Perfect. So then I think there's a question. We got to know about the maximum frequencies through Nyquist, but what about the lowest frequency? How low can one record with fiber and DAS?
Yeah, that's also a good question. That's a good question. It's a bit hard to explain it now without any further supporting material. So what I would offer is I would prepare a slide for tomorrow and talk about this in detail tomorrow.
All right. Looks like will be a busy day tomorrow, Philip, for you. All right. With that, I appreciate and thank you, Philip. So everyone who could join us today. The lecture, it's being recorded and will be shared later together with the material. So we'll see you tomorrow, Philip, and everyone else. Thank you. Have a great day. Bye-bye.